All right. So let's begin the second half. So our first speaker is Professor Jain. He is an associate dean in the MBA program and a professor in the practice of management. He joined Yale in 2012, where his research interests include the analysis and design of manufacturing systems, optimization algorithms, and probabilistic analysis of combinatorial problems. His recent work has investigated the impact of growing product variety on the manufacturing and designs of families of products, especially in the automobile industry. Without further ado, Professor
Jain. Good evening, and thank you, Etienne. I'm honored to be a stand-in for David Bach, who couldn't be here. Etienne was actually very gallant in saying to me that I was really very close as number 2. Perhaps he didn't realize that I might have felt even more honored if he had told me I was a distant number 2. So my talk today will be set in the context of the automobile industry, although the phenomenon I'll try to describe, the great proliferation of product variety, I think is germane to many product categories, from shampoos to smartphones and everything in between. And my message, I think, is a hopeful one, although this proliferation of variety is seen to be a huge headache by the manufacturing folks and everything upstream in the supply chain. The other sort of quick prefatory comment about my talk is that, at a place like Yale, what faculty teach in the classroom, of course, is informed by their scholarship and research. But every once in a while, this relationship gets inverted. And so the second title of my talk is to suggest that this work actually came unexpectedly out of things I was doing in the classroom, and you'll see if I get to it what that refers to. So just to quickly dive in, the automobile industry, especially in the US, was already quite mature by the 1950s. The US was producing something of the order of 8-9 million cars a year, and it was the dominant player in the global market for the automobile industry. And that history, that distinguished history, ended up creating some problems, especially by the time we got to the 80s. So let me just give you a quick sense of that. So this is a chart of the total sales, worldwide sales of light cars and trucks. The US is the bottom, dark blue. And as I said, already by the 1950s, this was a quite substantial portion of the global auto industry. And of course, over time, the Japanese, the Germans, the other European car makers, and eventually the Chinese have taken a big part of that. But if you go back to even as early as the 20s, the US had already begun to master the challenge of mass production. So back in the 1920s, the Model T Ford was being sold in over 2 million cars a year. And so the invention that Henry Ford had of a moving assembly line was quite consequential to the whole industry. And so this pattern continued for almost 7 decades, that essentially 2 or 3 or 4 models of cars accounted for nearly half the sales in the industry. This is from the 40s, Chrysler Plymouth. This is from the 60s. Just parenthetically, if you conclude that by the mid-60s, the US automakers had begun to lose their flair for design. I won't disagree with you. But what continued unabated for 7 decades was that just 3 or 4 models accounted for half the auto sales. So what the US automakers faced when they introduced a new model was the question of how many different plants should be used to produce this high-selling model. The typical output of a plant is of the order of 300,000 cars a year. And this mass production was a huge part of this process. Now, what does the situation look like today? So just quickly, fast forwarding to today, the top selling model today is selling only about 300 up to 400,000 cars a year. And there are almost 300 different models of cars sold in the United States. And so by the time you get to half the sales of the annual sales, you would go down to almost 30 different models. So we have posed the challenge now to especially the US car makers of deciding how many plants to use for a given model to how many models to make in the same plant, because for a plant to be profitable, you need a scale of approximately 200,000 to 300,000 cars a year. And that's becoming challenging if your plants are going to be dedicated to just one or two models. Now, the Japanese, just a parenthetical comment, the Japanese auto industry in the meantime had evolved in a very different way. Till about the 70s, the production volumes of individual car models were very small, 10,000, 20,000 cars a year. The Japanese government made sure that there was intense competition within the country, 11 different car companies, and they had to learn to be flexible in the same plant and make many different models. So if you took a snapshot of a Japanese auto assembly plant, even 40 years ago, or now, it would look something like this. Many different models of cars going down the line. If you look closely, there's a large car, the black one, there's a minivan, somewhat behind it is a small car. This would be, even now, infeasible in a US auto plant. The most flexible US auto plants can barely make 2 or 3 platforms of cars. So this proliferation of product variety has now created a huge challenge, especially for US car makers. But as I said, this is not just in the auto industry, this is pervasive across a number of industries. Okay, so my story is not going to unfold sequentially, because this is not where the story started. The story started in the classroom. I had really not thought about the auto industry. I was teaching a course on operations, and we were talking about the Japanese approach to manufacturing, the lean production idea, continuous flow, the evils of inventory and waste. And so I gave my students a question on a midterm exam to which I didn't know the answer. And I told them I didn't know the answer. They were smart, they would figure it out. So if you indulge me for a minute or two, I'll show you that question. So I said, imagine the simplest possible process. There are 2 products, yellow and green. There are 2 workstations, M1 and M2. And let's say the yellow takes 8 minutes on the first machine, 2 on the second machine. The green takes 1 minute on the first machine and 5 on the second. And let's suppose you need these 2 products in equal quantities. So what's the right batch size? Should you go green, yellow, green, yellow, green, yellow? That's a batch size of 1. Or should you go lots of greens followed by lots of yellows? And the Japanese tell you categorically, do the minimum batch size. Green, yellow, green, yellow. So I said, let's see what happens. So let's suppose you begin, so I'm going to call it Q. If your Q batch size is 1, you're going alternately green, yellow, green, yellow. The first green comes from the first machine, takes 8 minutes, and it goes down to the second machine where it takes 2 minutes. Now, because this line is without buffer inventory, the first green on the first machine is done in 1 minute, but then it gets blocked for the next minute because there is no place to put it. And only after that second minute does the green go down, the next unit of yellow comes in. And so if you do this repeatedly, every 10 minutes, you get a unit of each, yellow and green. So that's what I call a cycle time. And I said, okay, what if you have a queue of 2? What if you have yellow, yellow, followed by green, green? And the same chart quickly reveals that you get in 23 minutes, 2 units of each. So the cycle time has gone up from 10 minutes in the top case to 11 and a half. And in fact, if you increase Q, if you go 3 yellows followed by 3 greens and so on, the cycle time gets worse and worse. So the Japanese wisdom of small batch sizes actually also gives you the greatest throughput. So that's great. But then I said, so this is the case when the production times are as follows, 8, 2, and 1, 5. What if you distribute them somewhat differently? So you took the 8 and 2, and let's suppose it was broken 6 and 4 for the yellow, and you took the 1 and 5, 6 minutes, and it was broken 3 and 3. What happens then? Well, the bottom line is you do the same thing when the batch size is 1, the cycle time doesn't change, it's still 10. But now something interesting and surprising happens, that if you do 2 yellows followed by 2 greens, the cycle time actually goes down. So now in this case, a large batch size gives you the higher throughput. So I said, ponder the 2. In the first case, on the left, a small batch size is better from the point of view of throughput. In the second case, a large batch size is better. And I asked the question, when do you get one and when do you get the other? And I thought this was going to be a pretty straightforward question. So the students didn't get it, although in a 2-hour midterm, they had some creative answers. And it took me an embarrassingly long time to figure it out myself. The answer in this case turns out to be the following, that you look at two numbers. One is called the sum of column maxima. Look at each column, figure out the biggest number in each column, add the two maxima, and compare it to the sum of what I call the diagonal maxima. And if one exceeds the other, as in the first case, the column maxima exceeds the diagonal maxima, then q equal to 1 is the best. If the inequality reverses, then the other one happens. And you can write an expression for the cycle time. And so the students went on to more interesting pursuits. And I was stuck with this general question. If in this 2x2 case you had this sort of surprising behavior, what can you say about the general case? And you have M machines and N products. And so that led to a whole inquiry that came right out of the classroom and sort of preoccupied me for several months. And I was able to figure out some of the mathematics. It turns out to be both elegant and non-trivial. And so I'll just indulge you for 1 more minute with one particular answer, just to give you a flavor of that. So here is a larger matrix of processing times. The rows are machines, the columns are products. And the question is, if you go 1, 2, 3, 4, 1, 2, 3, 4, what's your cycle time? To get that answer, you have to do a slightly more involved computation. Just to give you a flavor of it, here's what you do. You construct a graph where each node corresponds to a processing time in the matrix. The weight of the node is that processing time. And you construct a network in which you connect all these nodes with the right horizontal arcs, with all the down vertical arcs. And you have some diagonal arcs that come into a node from 1 level below, 2 to the left, 1 level below, 2 to the left. And you also have arcs coming in 2 below, 3 left, 3 below, 4 left, etc., until you run into a boundary. And on this graph, you compute a path of length 4 nodes that have the maximum total weight. So for instance, going across this way is a path of length 4, something like this is a path of length 4. Of all of these paths of length 4, what's the one that gives you the highest weight? And that turns out to be this one. And that sum, 27 in this case, is the cycle time. So anyway, there's a lot that you could do with the sort of underlying mathematics. And I was giving a talk about this at a conference, scientific conference, and in the audience was a scientist from General Motors who, I think I need to wrap up soon, who said, have you thought about the auto industry? And I hadn't. So that led to a long and I think mostly fruitful collaboration with the General Motors research labs funded by the National Science Foundation. And what we ended up doing, I'll skip through this, was to show, so I'll conclude essentially with the slide to say that what manufacturers think of as a headache and a nuisance, that you have 16 products. This is actually data from one of the engine plants. 16 products, 5 machines. And this is a headache. But what we suggested was that you can actually exploit the natural complementarities that exist in the data to gain productivity. And so that's what the chart on the right shows, that if you judiciously combine subsets of these products, you can gain productivity improvements. And this is the final message that I hope to leave with you, that this proliferation of product variety is not always a headache. It can actually give you the opportunity to make productivity gains. Thank you for your patience.